Okay, I guess we can start. So the audience is kind of small today, but highly qualified. So it's a pleasure to have Michele Caselli, who is a postdoc at the University of Sydney, and this year is actually visiting Princeton University. He's going to talk about the existence and regularity of minimal surfaces, but non-local minimal surfaces.
Thank you.
Please.
So thank you for the introduction, and really thank you for inviting me here. It is an honor for me being able to speak here at the IAS. So, okay, today I will speak about a series of works, which are mainly two works. All the works Codimension 1 are joined with Eric Florid-Simon and Joachim Serra, both from ETH in Zurich. And then I will say at the end something about the Codimension 2 case, and these are joint works with Mattia Freguglia from the University Bocconi in Milan and Nicola Picenni of the University of Pisa. Okay, so the motivating problem of all this business is the following, which is simple to state but not simple to solve. So is whether in any closed and dimensional Riemannian manifold with dimension less or equal than 7, there exist infinitely many smooth embedded minimal surfaces. Okay, so this was the case n equals 3. So for free manifolds, it was problem 88 in Yau's famous list of open problem, maybe in a slightly different form. I think in the original version here it was immersed, but now we know that actually they are embedded. And today we focus on the case 3 and 4. There is no real reason why what I'm gonna speak about does not hold like from 5 to 7, but there is one step missing, and you will understand where it.
I ask what about
sure.
N less than 7? Why is that in there? Why is that?
It's just because we know that for n greater or equal than 8, these are not smooth. There are minimizing minimal surfaces that have singular parts. Yeah, exactly. Yeah.
But that doesn't mean there aren't smooth ones.
Sorry?
I mean, so there are singular ones, but
sure. Yeah, exactly.
There could be smooth ones.
Sure. Yeah.
So
let's say that
it doesn't mean it can't be true for.
No, but okay, you will see. So so we propose a way to approximate minimal surfaces that in some sense is an approximation of smooth minimal surfaces with smooth objects. Okay. So like for what I'm gonna do, this is the setting. Okay.
But it might well be true that there are infinitely many, only it's possibly extremely hard to prove because when you minimize, you might actually see a singularity.
Yeah, exactly.
And infinitely many, that puzzles me a bit what you mean by infinitely many as well. I mean,
infinitely many, like,
are they distinct in some way? Or?
Yeah, geometrically distinct objects.
And they're codimension 1, you mean?
Yeah,
surfaces.
Smooth embedded codimension 1 submanifolds.
The geometrically distinct is what?
Okay, I just mean that I'm not allowing that you count the same twice to count 2 guys, right? So, okay, if I put smooth and embedded, this should be remove geometrically distinct. If they're smooth and embedded, they are distinct. They have okay, it's not true that they have a different area, but the way I will construct these objects is by objects that have a different area. Okay, so they are
different sets.
Yeah, exactly. They are
that's the question.
They're just different sets, literally, right?
Yeah. Okay, thank you. To construct, so in any way, if you construct infinitely many minimal surfaces on a Riemannian manifold, on a closed Riemannian manifold, you are forced to consider unstable critical points of arbitrarily large index. And this can be seen already from sort of simple examples. This is just a result, an example result by Chodos, Ketover, and Maximo, that if you take a 3 manifold with a bumpy and positive scalar curvature metric, there exist only finitely many smooth minimal surfaces with bounded index. Okay, so if you construct infinitely many in some way, you have built minimal surfaces with arbitrarily large. Okay. So you have to find them by a min-max scheme in some way, unless the proof is non-constructive. Okay, so now the Yau's conjecture is solved. It was solved first in the case of generic metrics by Iri, Marquez, and Nevers in 2018, and then by Antoine Song in full generality. But both arguments are non-constructive. Okay, so the first paper is, I would say, very non-constructive. So the proof is by contradiction nonsense. And the second one is a bit more constructive. So it splits the proof in a constructive part, and then but there is a crucial contradiction argument even in songs.
But are they using minimax arguments or?
Sure, yeah. They both use min-max argument. But in the first one, in a very indirect way. It uses the Weil law for the spectrum of minimal surfaces, and it just finds a contradiction. If there exists only finitely many, it finds a contradiction in the Weil law, but perturbing the metric. Okay.
Yeah. So, this is a random metric or what?
No. Because this first paper is for generic metrics. So it's not for every metric. There exists infinitely many minimal surfaces. I mean, a posteriori, they do exist for every metric. But this first paper by contradiction is just for generic metrics. Okay. So the basic problem is that people in minimal surfaces know that minimal surfaces with bounded index are non-compact. Okay, non-compact, I'm vague in what this means, but I will explain more in the details later, but are non-compact in the sense that you have to consider weak topologies to extract subsequential limits. And so if minimal surfaces with this property are non-compact, let alone min-max sequences when you try to construct them, right? So, and the problem, one of the problems, there are many problems, but one of the problems can be seen even in R3. If you take a sequence of shrinking catenoids, this is a fixed minimal surface with index 1. And then you converge, you can shrink in catenoids, you converge to a plane with multiplicity 2. And this is what could happen in an ambient Riemannian manifold, right? And the problem of this is that, so then to extract subsequences, you are forced to consider very weak topologies, like varifolds or this kind of stuff. But then how can you be sure that the limit object is a geometrically distinct surface, right? Because if you take limits and you allow the multiplicity to count twice, then even if I tell you a recipe to construct this kind of weak objects with different mass or area, how can you be sure that they are geometrically distinct? And this is, in the classical case, is solved by tricks. I mean, it's not solved by easy tricks, but it's usually when the business of either generic metrics or multiplicity one conjectures comes into place. Okay. So now we come to what we do. We propose to bring a different approximation of minimal surfaces, in this case of ambient Riemannian manifolds. So we consider what is called the fractional perimeter that on Rn has been introduced by Caffarelli, Roquejoffre, and Savin in 2010, and study the critical objects for this functional. So the main purpose of my talk today is to show that whatever this object is, so whatever the fractional perimeter is, we show that this is sort of an ideal object to apply min-max methods on it, in the sense that, like, Morse theory for the fractional perimeter is almost flawless, like finite dimensional Morse theory. Okay. So, for example, fast forward 10 minutes, one of the results that we are able to prove is the following. Take a three-dimensional closed Riemannian manifold and take a sequence of S minimal surfaces, so critical points of the fractional perimeter, with uniformly bounded index in a weak sense. Then up to subsequences, they converge in the strongest possible sense of submanifolds. Okay.
Will you tell us what this S minimal is?
Yeah, I will tell you the definition later. This is just a fast forward as an example theorem. Okay. So this is to say that for us, not bad things happen. You cannot pinch, you don't have multiplicity issues and this kind of stuff. And one can even recover classical minimal surfaces by sending back S to 1. And I will tell you more about this later. Okay, so this is the definition of the fractional perimeter. You fix a parameter from S S between 0 and 1, you fix a set in a Rn on in a Riemannian manifold. On a Rn, the fractional perimeter is defined as this interaction energy, okay, which is the HS/2 seminorm of the characteristic function of A. Okay, and the definition is the same on a Riemannian manifold. I mean, there is a suitable kernel that depends on the heat kernel of the manifold, but whatever this is a sort of BV type perimeter where you put the fractional Sobolev-Slobodevsky spaces here. Okay.
Yeah. Okay.
Okay, no, if you have questions, please interrupt me. So, I think the first time you see this definition, it's good not to think too hard about the definition, but to see what are the properties of this object. Okay, so the first easy property is that if you fix a set and you multiply by 1 minus S, and the set is decent, like finite perimeter or smooth, this converges to a constant that depends only on the dimension times the perimeter of E. Okay. So this is true even in the sense of gamma convergence by a result of Ambrosio, De Filippis, and Martinazzi. Okay, so we will focus on the study of critical points of this functional. Okay, so I will call a set an S minimal surface if it is a critical point for the fractional perimeter for inner variations. Okay, so I move the domain by vector fields. And if the first variation is 0 for every vector field, then I say that this is S minimal surface.
Well, how are you moving the domain under what?
Yeah, sorry, this is the flow. You fix a vector field, and this is the flow of the vector field at time t. Okay. So I'm moving the set, if you want. I'm moving the set in the domain, and I ask that this first variation is 0. Okay.
But what are the conditions on the vector field? No particular conditions?
Smooth. If you take a compact manifold, smooth. Yeah. C1. I will say that a set is stable as minimal surface is the second variation is non-negative. And we also have a notion of a weak notion of Morse index that you can just think about it as the Morse index, but I think to see the definition is a bit cumbersome. So okay. A suggestion that is very important for later is the following. So take a set, okay? Take a set and consider this function. So consider the characteristic function of E minus the characteristic function of the complement. And this is a function that goes from the manifold to plus and minus 1. That I want you to think about the boundary of the one-dimensional ball, so like the zero-dimensional sphere, okay? With this notation, the fractional perimeter is an absolute constant that is like 4 or whatever, yeah, times the HS/2 seminorm of this function. Okay, so for codimension 2 and higher codimension, I think it's very important to think S minimal surfaces as these maps, which are stationary S/2 harmonic maps into S0, into the sphere, and that are minimizing outside their singular set. Okay, this will be essentially the correct definition in higher codimension. Okay, so imagine, actually this is also true. So if you embed S0 in S1 and you take this function, this is actually a weakly S/2 harmonic map with values in S1. Okay, but this will be clearer later. Why I suggest to think about this, yeah, I think you can think about it this way, that in some sense, S minimal surfaces are like the codimension 1 version of harmonic maps in this way, okay? So with this definition, we can prove a theorem that is as follows: fix any dimension greater or equal than 3 and take an n-dimensional closed Riemannian manifold. Then for every integer p, there exists an S minimal surface with index less or equal than p for this weak notion of index.
And S is less than 1, or?
Yeah, S is between 0 and 1, sorry, but you always can imagine S very close to 1 when like the fractional perimeter is close to the real perimeter, to the real area, okay? With the suitable growth, this is in accordance with Weil law and the expected growth of the fractional volume spectrum, in the sense of growth. And the important part is that for n equals 3 and 4, these are smooth. We know these are smooth. Okay. The existence per se, so not the regularity, the existence follows a similar construction by Chodos and Mantulidis and Gaspar Guaraco. And we use the fractional Allen-Cahn equation to construct the critical points. I don't think that we really need this. So I think that if we would have been experts in min-max, we could have done min-max without the fractional Allen-Cahn equation, but it's handy to have a... So we use a very general min-max theorem that you can find, for example, in Gossub's book, to construct infinitely many solutions of the fractional Allen-Cahn equation at a growing index, at an arbitrarily large index and different energy. Okay.
So will you ultimately use this to get minimal surfaces?
You can do this to get minimal. So you can do the classical version of this, but there is a real issue when you send epsilon to 0. So for fixed epsilon, like this is fantastic. So the functional satisfies the plasmic condition. You have a critical point for every p, and exactly index p.
That becomes very singular, of course. Yeah.
Yeah, exactly. But when you send epsilon to 0, to be able to like recover real smooth minimal surfaces, this is very hard. And for example, in this paper by Chodos and Mantulidis, they solved this issue for 3 manifolds and generic metrics, but this is a very delicate step when you send
the generic metric.
Yeah. And so they prove the multiplicity one conjecture for this kind of limits for generic metrics. So generically they have multiplicity one, then they know they are smooth on 3 manifolds. Okay, so probably the key part, the key non-trivial part of our result is the following, is that if you take a sequence of solutions to the fractional Allen-Cahn equation with index bounded by p, then we can bound the BV norm. Imagine this as the perimeter of the nodal set. Okay, we can bound this, the BV norm of U epsilon as, okay, imagine even R equals 1. This result is interesting. I mean, there's no point in the manifold, not the manifold. Imagine R equals 1. You can bound this by a constant that is independent of epsilon times R to the n minus 1. And this is very bizarre because if you... So the set version of this theorem is the following, if you want. So that let me state this theorem for surfaces. Per surfaces, this means that if you take E... But let me even say in Rn. If I take E in Rn, which is an S minimal surface with index E less or equal than n, then the classical perimeter of E in B1 is uniformly bound. Okay. And this is bizarre, okay, because it's saying that, so for example, why this is not true for classical minimal surfaces? You can have very stupid examples. Take B1 and take arbitrarily many hyperplanes, okay? And then you can make these as big as you want, and this is whatever you want, stable, locally minimizing configuration, right? So this theorem and also our theorem for the fractional Allen-Cahn equation is saying that for the fractional setting, if these layers are too close to each other, then you are unstable. Okay, and actually not even unstable, then you have infinite index. Okay.
Probably you said this, but I forgot what the index is. What do you mean by the index?
Okay, so in this setting for the fractional Allen-Cahn equation, I mean the number of negative directions of the second variation. This at the like for the functional defined on H1 of n. HS, okay. So this at the level of Allen-Cahn is the standard notion of Morse index. Okay. Then we also have a weak notion of index for surfaces that it's weird just because if you don't know that the surfaces are smooth a priori, we give a weak notion of index and we use the finite index property to prove smoothness. Okay, so I don't want a notion of index that uses the second variation formula, but knowing a priori that the surfaces are smooth. I want to use the finite index property to prove that the surfaces are smooth. Okay. And as I said, this result is bizarre because so you can control a seminorm that is strong, uniform in epsilon, you can control a seminorm that is stronger than your energy space. And the fractional Allen-Cahn equation has is a semilinear elliptic PDE, but the right-hand side blows up as epsilon tends to 0. So there is really something weird going on in the non-local interaction in this result. And the proof exploits this. Okay. So for us, since I control uniformly my maps in a stronger space than the energy space I am in, for us we have a super precompactness of these sequences. So when I send epsilon to 0, I know that all the Allen-Cahn energy that I have converges to the perimeter of the set U equals to +1. So for the fractional Allen-Cahn, the function converges to just +1 and -1. It has two phases and concentrates. And so the potential part goes to 0 of the energy. And this is something that does not happen for the classical Allen-Cahn.
They actually balance.
Yeah, it can, exactly. You can have energy balancing, but this is one of the problems is also that the energy can drop, right? Because the potential part does not tend to 0. Yeah. And so that in the limit, it's hard to distinguish the surfaces, even if you knew that they had different Allen-Cahn energy before the limit. Okay. So let me sketch the proof of the BV estimate, because I think even at the end of the proof, we prove a covering theorem that I think is very nice and of independent interest in maybe other things in analysis and this kind of estimate. So we know, so assume that you know that this is true for stable. Okay, we know by a paper by Cabré, Cinti, and Serra that if you have a stable solution in B1, then you can control the BV norm uniformly in epsilon. Okay, so this is already non-trivial. Okay, this is already non-trivial, but because as I told you, this configuration for the classical perimeter is stable. So this result is already saying this for m equals 0, and so it's already different from the classical case. Okay, but even assume that this is the case. Okay, and we try to extend this to finite index. Now, one problem of the fractional Sobolev spaces is the following: is that index less or equal than m does not imply that your function is stable in one out of m+1 disjoint balls. So for the classical Allen-Cahn, this is sort of trivial. So if you were unstable in m+1 disjoint balls, then since they have 0 scalar product, then you have m+1 independent negative directions. Okay, so the proof is one line for the classical. But contrary to the classical setting, in the fractional setting, having disjoint support does not mean that you're orthogonal in HS. Okay, and this looks like a sort of pathology, but we really exploit this as the thing that makes the argument work, in some sense. So what is true in the fractional case is that if the index is uniformly bounded by n, then if you take disjoint balls, U is lambda stable in one of them, and I will tell you what lambda stable is in a minute, but you can just think that lambda equals 0 is classical stability, okay? And this is just a weaker notion of stability, where the constant lambda is the minimum of the distances between the balls at a suitable power, okay? So it is true that you have some sort of control on the second derivative if you take m+1 disjoint balls, but the negative constant sort of degenerate when these balls are close to each other. Okay, so the definition of lambda stability is the following: take the Allen-Cahn energy, the fractional Allen-Cahn energy, which is this one, is very simple. So you have the Sobolev term, and then the Allen-Cahn potential term is not even that important what you put here. You know, this business, you can have basically any potential that vanishes in plus or minus 1 and have some plan. decent properties. Lambda stability is the following property, is that the second variation is greater or equal than minus lambda the L1 norm of phi squared. Okay, so lambda stability is like you control the second variation from below by a weaker norm of the test function. Okay. So as I told you before, we knew that for stable, the uniform BV estimate is true. So take a stable solution of the fractional Allen-Cahn equation, then you have a uniform BV estimate independently of epsilon. So the Allen-Cahn version of this result for surfaces. So the first thing that we do, but that is not the surprising one, I would say, is that we can squeeze this result to lambda stability for a small constant. So first, we are able to say that if you are lambda stable for a small lambda, that depends only on the dimension and on S, okay, then you have a uniform BV estimate. But this, you can just buy that this is sort of squeezing this proof as much as you can. Okay, you can just reabsorb the terms, and this is a minor improvement that you get. But the big improvement that we have to get is the following. So, okay, together with the fact that if the index is bounded by M, given M plus 1 disjoint unit balls, then U is lambda stable in one of them, where lambda, I told you, is an absolute constant over the minimum distance between the balls. So let me draw a picture over to the N plus S. So if I have, I think there is the picture in a moment. Okay, and then this result, the second one, so if you're lambda stable for a small constant, then I have the BV estimate, means that if I have the balls and if they are sufficiently far, okay, then I have what I want, okay? But then this business becomes like a problem that has nothing to do with surfaces, or is like a covering problem about, okay, there should be a picture about the set here, but whatever. So imagine here there is like a set that is a set E that is green somewhere and black somewhere else. Okay, and you don't know anything about the set. So if I told you the following property, so take M equals 3. So I'm just dealing the case like Morse index 3. 2, actually, Morse index 2, sorry, M equals 2. If I told you that the following property holds. So if you take 3 balls, each of the ball at pairwise distance greater or equal than an absolute constant d0, then I have a uniform perimeter estimate on the set E in half of one of these balls. Okay. Does this imply a local uniform BV estimate everywhere? And the answer is yes, but the argument is not trivial. You have to like run a precise recipe to show that if a set, but not even a set, imagine here you have like any subadditive function of balls. If I told you that you have a subadditive function...
So this is for any 3 balls, or with this distance property?
Yeah, exactly. But if I told you that you have a subadditive function on balls on Rn that have this property, so for every 3 balls, if they are sufficiently far from each other, then you have the estimate that you want in half of one of these balls, then we show that this implies a uniform interior like B1 to B half estimate. Okay. But
so what is D0? That's
this is the pairwise distance.
I understand that, but you can let D0 can be. There exists a D0, or I didn't know.
No, D0 is fixed.
Exactly, D0 is fixed by this result of ours. So, okay, in our setting, lambda is like 1 over D0 to the N plus S.
Okay.
So D0 is fixed very big. Okay.
Yeah.
And this is our proof is inspired by a paper by Figalli and Zhang on a sort of similar problem on finite Morse index semi-linear elliptic PDEs. But I think that, so for me, this covering theorem is surprising, even if the proof is like, once you read the proof is not hard, but the statement, the thesis, the hypothesis and thesis is somewhat surprising. So the long story short is that we have a uniform BD estimate for solution of the fractional Allen-Cahn equation, either on Riemannian manifold or Rn for every dimension. Okay, now back to our existence and regularity theorem. So note that in our setting, there is no place where we prove a multiplicity one conjecture as in Chodos-Mantoulidis, okay? And this is just because once you do the min-max scheme and I construct critical points of the Allen-Cahn equation at different energy levels, we know the continuity. So we send epsilon to 0. In the limit, you convert to a set whose boundary is smooth and is an S-minimal surface, and it has different fractional perimeter. So there is no place, it's not really that we address the multiplicity one issue. In our setting, there is no multiplicity issue. And this holds for every metric, by the way. And also in the process, we can show the finite Morse index version of the Bernstein theorem for fractional minimal surfaces, and also of the De Giorgi conjecture, like the finite Morse index version of the De Giorgi conjecture for S minimal surfaces for n equal 3 and 4, which is this is the Bernstein one. So if you take in Rn for n equals 3 and 4, take a smooth finite index S minimal surface, then sigma is flat. And this, for example, means that the equivalent of fractional catenoids, they do exist, but they have infinite index. And this, you can think about it as like the heuristic reason of why we converge smoothly, because you cannot pinch out a catenoid. Because you can pinch out a catenoid only if you have infinite index.
I don't understand what does sigma equals.
Sigma is the boundary of a set. So E is a set.
E is a set.
And sigma is the boundary. So sigma is an n-1 dimensional smooth hypersurface in Rn. Okay. With finite index. And C2, if you are S minimal and n is 3 or 4, then sigma is flat. And this is very different from the classical case, right? Because a catenoid does not satisfy this property for the classical area. As an index 1 is smooth and it does not satisfy this. Okay, so the proof of this fact highly relies on the BD estimate plus things that are known in literature. Let me just assume n equals 3 and sketch the proof, because I think you can see that there are very similarities with the classical minimal surfaces and regularity of the Giorgi business. So take my surfaces and blow them up to like consider 1 over KE. This converges in L1 log intersected the energy space. Okay, so the BV estimate implies continuity in our energy space. So we know that this set converge in the energy space. The perimeter cannot drop. So the fractional perimeter in this process is not lower semi-continuous. It is continuous. Okay. We prove that the finite Morse index cone is stable outside the origin. Okay. So, okay, by the way, there is also a monotonicity formula for S minimal surfaces that is completely equivalent to the monotonicity formula for classical minimal surfaces. So you know that blow-ups and blow-downs are cones. Okay.
So I understand nothing. EK is, what do you mean 1 over KE tends to infinity when K is going to infinity? I don't know.
Converges.
Yeah, it's going 0.
Yeah,
0 goes to 0 or what is it?
No, K goes to infinity.
No,
K goes to infinity. So
You're rescaling.
Yeah, exactly. I'm taking a blow up of the set, right?
You're just rescaling your surface, right? Applying an homotity.
So this is like a real number times the set.
Yeah.
Oh, okay. If you want, maybe take a point in the boundary of EK and assume that 0 is in the boundary of this way. But I'm really just saying that if this is E, I take a point here, I take a small ball, and I just rescale the set. Okay. And the point is that, so you converge to a cone, and then it becomes an issue of classification of cones, right? Once you have an improvement of flatness theorem, and I will say something about this later. So we prove that Feynman-Morse index implies stability is not as easy as trivial as in the classical case, because as I told you, functions with disjoint support are not orthogonal, so there is an argument for this. It's not completely trivial, but okay. Now, there are two possibilities. Either the cone that you get has a smooth link on S2. Okay, we're in 3 dimensions, right? So I blow up, I get a cone. So if the cone has a smooth link on S2, then there is a classification of cones of stable as minimal cones in R3 with smooth link. Okay, so the thing that you have to rule out is if the link on S2 is not smooth. Okay, so you have to rule out cones that are like across times R. Okay, and this is very classical. Then if you blow up at a singular point, okay, you split the factor R. Okay, and so you have essentially to rule out cones of this form in 3 dimensions. But this can be done by the stability and the BV estimate and the finite index quite easily. So for a smooth S minimal surface, this is the stability inequality. Okay, if sigma, which is the boundary of E is the set and sigma is the green part, if you want, sigma is in a 2-dimensional surface and E is the cone. If sigma is the boundary of E is a stable S minimal surface, then this property holds, and you can compare this with the classical stability inequality for minimal surfaces, which is like minus whatever.
What is N as X?
Yeah, is the outer limit normal, but I will say. So this is the classical stability inequality for minimal surfaces, where this is the second fundamental form. Okay, and there is a fractional version of this that is basically the same. So N is the outer unit normal to the set. So this is really like the HS/2 Sobolev energy of the outer unit normal. And by the way, it's true that if you fix the surface, you multiply by the right thing and you send S to 1, the left-hand side converges to the second fundamental form times phi squared. Okay. And this is bounded by the fractional energy of the test function. Okay. And now you can imagine this is not how the proof goes, but I think it shows why it works. If you multiply by 1 minus S and send S to 1, the HS, this Sobolev energy converges to the H1 energy in B1, and this converges to the H1 energy. But if you just fix the test function with this sort of a bump that is 1 close to the origin and then 0, this term is uniformly bounded by our BV estimate, because this is just, we know that sigma is like a cone in R2 cross R, but since we have a uniform bound on the classical perimeter of sigma, then this is uniformly bounded by like 2 times the BV constant. Okay. But you can see that if you split a dimension, then the H1 semi-norm of the normal, so like the L2 norm of the second fundamental form, is infinity if you split the factor. Okay. So this is
because the normal has a jump.
Yeah, exactly, because the normal has a jump. And this is not
so
the
it
case.
Cannot be in H1.
Exactly. This is not the case if the link on S2 is smooth. Okay. So there, this is finite. Okay. But if you split a direction that this is infinite and we have a uniform bound of this coming from the stability and the BV estimate. Okay. But more or less, the proof goes on the same as you would do for classical minimal surfaces. And this, together with the fact that we have an improvement of flatness theorem, so we know that blowups are unique. Okay, then we can. It gives us the classification that we wanted. This one. Okay. Okay. So now just one slide about the recovering classical minimal surfaces. So these are not papers of mine. Okay, so I'm not spending gonna spend a lot of time on this, but by the union of these two papers, by Ciandi, Pierro, Serra, and Baldinoci, and another paper by Eric Florit, in 3 dimensions, if you have a sequence of stable or finite index S minimal surfaces, then you can send S to 1, and you have uniform curvature estimates with the constant that does not depend on S, uniform estimate on the classical mean curvature of this object. And you get back classical minimal surfaces as S tend to 1. So you can think about our approximation like a sort of a priori version of minimal surfaces. So we define an object that is a weaker energy, okay? But for some reason, we get that the critical points of these objects are smooth, even more regular than in the classical case. And then we send back S to 1, and we recover smooth classical minimal surfaces. So it's just that we approach minimal surfaces with the functional that is well behaved for min-max. Okay.
So it's not creating multiplicity?
No, you have uniform separation estimates. Okay, so sheet by sheet, yes. So you know that at each point, the two sheets can be separated by a factor of root 1 minus S.
Oh, okay.
Okay.
Okay, but you're using stability somehow, right?
Yeah, exactly. Yeah, sure. Yeah.
So finite index could still create.
Yeah, exactly. Stable does not. So,
but finite index could still create.
Yeah. A finite number of points that is like not really singular.
I mean, you could still, you're not avoiding the catenoid as like, you're sending S to 1 by your method, right?
No, I think you like.
Are you recovering?
I think you can only touch more or less because like you can only, I don't know how to say. So you can only have like 2 sheets that they touch at the point in the end.
But so you're telling me that you recover the multiplicity 1 conjecture without.
Which multiplicity 1 conjecture?
Okay, so you run the minimax. Okay,
yeah.
So you find different sequences of S surfaces.
Yeah.
Okay, with different indices.
Yeah.
Okay, so now you say take a sequence of your surfaces with index 2.
Yeah.
You're telling me that you're converging to a classical minimal surface without having any point singularity?
No, outside 1 point of singularity.
So on that point you can have. On that point, you might have the catenoid.
I mean, but you have like smooth conversion with uniform curvature estimate everywhere.
If you're stable.
No. This also holds for finite index.
So you've proved Chodosh-Mantoulidis in another way.
In this paper by Eric Florit, he recovers the Yau conjecture and even the
that was my question.
Equidistribution and density and the Weil law, everything for classical minimal surfaces. Like he sends back S to 1 and he recovers all these results about classical minimal surfaces.
But you're not using any bumpiness or genetic metric like Chodosh-Mantoulidis.
No, I mean, when you send back S to 1, so it depends what you want to prove, right? So in the paper by Enrique, so you know that you prove that the P widths are achieved by smooth minimal surface, by smooth minimal surfaces, okay? So integer multiplicity times union of disjoint smooth objects, okay? But then when you want to prove like for example, the density or the equidistribution, then these are stronger results and you need the bumpy method, the bumpiness of the method. Okay. So if you want, he proves that
But I'm sorry, so what would be wrong with the following?
Sure.
Okay, so give me a catenoid.
Yeah.
Okay.
Classical
catenoid.
Yeah, sure.
Okay. Approximate the classical catenoid. I mean, sure, you can approximate the classical catenoid with ES minimal surfaces, right?
No, you cannot.
Even just the classical catenoid, the normal one?
No, because
you cannot.
Fractional catenoids have linear growth at infinity. It's completely different.
So even locally, I cannot.
Yeah, exactly. Yeah. So the catenoid has logarithmic growth and fractional.
No, but forget about the catenoid. I mean, say that I give you, so you're just telling me that by this method, you will never see any degeneration in your sequence whatsoever. So,
I mean, I think that the only degeneration that you can see is that two separate uniformly bounded sheets touch each other at the end of the day in at most index points, number of the most index points.
in at most?
So if you are index P at the most P points, so does not happen for stable, right?
What do you mean by at most? I mean, like these guys have the maximum principle, right? So if they're touching at P points, then you're touching everywhere.
No, because the maximum principle for like fractional, you need that the set is.
No, but the final guy, the minimum surface, has the maximum principle, right? So
yes.
So if I have two sheets,
no, sure, you're right. Okay.
So it's not a problem of finitely many points, right? I mean.
Okay, so I'm sure that these surfaces, the surfaces that you create in this way, are smooth away from a finite number of points that is the Morse index. Okay.
And so far, I was perfectly happy with the statement.
Okay.
But then you're telling me that at those points, you can't see a catenoidal neck, which is becoming smaller and smaller. So what can you see then at those points? Because then, the singularity is removable, so it's just completely smooth. So why would you need these exceptional points? That's
okay.
I thought that is where the index is going to kind of hide, and you could possibly find the catenoidal neck in the limit.
Yeah, I think that probably you're right. Now I'm puzzled by this. Yeah, I think that you're right. Yeah.
I mean, because it can happen in these min-max arguments. I mean, it's
sure,
not,
sure.
It could happen that you see, say, a double cover of the sphere, which is becoming better and better, and then it converges towards a stable sphere, right?
Yeah.
For minimum surfaces.
Yeah.
And somehow what I would have naively thought is if you make the neck of the approximating guy not too big, like, finite, for S sufficiently close to 1, you should be able to approximate this almost double cover of the sphere.
I see what you mean.
With an S minimum surface,
sure.
And then I take a diagonal sequence, right? So this can happen.
Okay, I see.
Okay. Oh, well, now I mean, my picture is reconciled.
No, and I'm sorry also, these are not papers of mine, so I know what it is.
Just to understand.
If you read the statement, it's quite technical.
Just to understand.
Yeah, I think this can happen.
I mean, it's still extremely interesting.
Sure. No. Yeah.
Okay.
So it does not necessarily give you smooth minimal surfaces, though, because of this problem.
Well, I mean, there are those. I mean, it doesn't give you smooth convergence except on these kind of exceptional points, right? I mean, at those exceptional points, you could still converge smoothly, possibly. I mean, like, the final object could still be smooth, but maybe your convergence is not.
But in the end, do I have a nice smooth minimal surface?
I still would think so,
sure,
because the singularities are removable anyhow. It's just that your guy is not converging nicely.
Okay.
Yeah.
And of course, then this is also the way you pick a multiplicity in a non-trivial way in the limit, right? I mean, your guys, maybe they are connected at multiplicity 1, but because they kind of almost double cover, they converge to multiplicity.
But the multiplicity issue doesn't really arise here, or?
Sorry?
The multiplicity issue does not arise.
No, I think it still arises.
What multiplicity issue?
Well,
that you could converge to a double cover of the sphere, for instance.
No, sure, okay. Yeah. I mean, when you send S to 1, that you can convert to a smooth minimal surface with
multiplicity.
Okay.
It still happens.
Right.
This has to happen.
Yeah.
Somewhat.
okay.
Because the final theory is, susceptible to this kind of behavior.
This, I think, is as good as it gets. I mean, it's not
Exactly. So that
was
expected
that you can get something.
And the only way you can get rid of this is by making generic assumptions on the metric, right?
I mean, a posteriori, the result is true even without the generic metric, but this is like with the constructive proof. I'm not aware of a result that. So a posteriori, you know that infinitely many smooth, embedded, everything exists in every three-dimensional.
But that's not constructive.
Yeah, exactly. That's not constructive. Yeah. Okay. So the part two, but I will be very, very brief on this. So we are trying to set the ground for the Codimension 2 version of this approximation. And in a work with Mattia Freguglia and Nicola Picelli that is already on archive, and another one that will be published soon, like in 1 month. So as a first step, we did the sort of oriented version of the Codimension 2 area, which is the setting of currents. Okay, so we define a fractional notion of like Codimension 2 perimeter, okay, on currents, okay, which is the following. Okay, this is the basic that you need to define this object. So you take a current that is a boundary, okay, and is a boundary of an n+1 dimensional integer rectifiable current with finite mass. But we don't ask that its boundary, so the Codimension 2 guy, has finite mass. But this is clear, right? I mean, doing something else would be like defining sets of finite fractional perimeter only between sets that have finite perimeter. Okay, if you define a different energy, you cannot ask like in the definition a stronger.
That is +1, right?
Where? Sorry.
N plus.
Yeah, sure. Sorry. Yeah. This is a +1. Yeah. Okay, so this is you take an n-2 dimensional object. Okay.
It's n-2 dimensional, so that one is n-1 dimensional. Okay. Because n is the dimension.
No, yeah, okay, sorry, exactly. Yeah.
N is the dimension of the ambient, so sigma is dimension n-2, and T is dimension n-1.
Yeah, so you can imagine this picture. So sigma can be like a closed line, a closed curve in R3. Okay. And T is the expanding surface of this. Okay. But then we define this energy space, which is it's fractional Sobolev maps, more comment about this exponent later, from the manifold or Rn to S1, okay, with prescribed Jacobian n-2 current equal to sigma. So the Jacobian is just the current that is dual to this distributional form, okay? So you can think if everything is smooth, so if U is a smooth function from the exterior of sigma to S1, then the Jacobian is sigma times the degree of U around the surface. Okay, so this is like a winding number definition, but very weak. Okay, actually, this definition has a catch that is a little silly, but I don't want to go into the details. That functions in H1 plus S over 2 do not embed in W11 lock. And so this guy does not make sense, and this is not even a distribution. So there is a delicate point in writing this definition compared to, for example, W1P here for P strictly less than 2. Okay, so that's a delicate point. And then we define the fractional mass as the infimum of the fractional Sobolev energy over the maps with prescribed Jacobian. So on Rn, this is the fractional Sobolev energy. So for m equals Rn, we are minimizing this energy, okay, with the suitable kernel on Rn. And we also know, okay, but this is very easy, that there exists a minimizer, so this is actually realized by potential. Okay. So now recall the point of view that I told you about the Codimension 1 fractional perimeter, which is recall that I ask you to think of S minimal surfaces as maps that are S over 2 harmonic with values in the zero-dimensional sphere. So actually, if you take a minimizer of this energy among maps with prescribed Jacobian in this way, you get a stationary weakly harmonic and minimizing S harmonic maps with values in the unit circle in the exterior, okay, in the exterior of the support of the current, okay. And also with something else, with vanishing Jacobian outside this prescribed singular set. And indeed, in our procedure, we sort of do an improvement of regularity for minimizing fractional harmonic maps with vanishing Jacobian. Okay, but I think that this is the correct parallel to codimension one. So at the end of the day, what also the fractional perimeter is doing is prescribing the singularity and giving you the stationary or weakly harmonic map with that singularity that is minimizing outside. And if you do this in codimension one, you get two constants, plus and minus one outside. And so you get the definition of the fractional perimeter. But in general, in codimension two or in general codimension, this is what you're doing. Okay. So in this setting, we are able to prove that this functional gamma convergence to the classical mass on currents. And we also have equicursivity. So with respect to the flat topology, sorry, the integer flat topology of currents, okay? With respect to the flat topology, we also know equicursivity. So if the left-hand side is uniformly bounded for a sequence sigma s, then the subsequence converges flat, and the limit is rectifiable and has finite mass. And in doing this, we prove many other things. So an isoperimetric inequality, we prove the first variation for this object that also recovers the first variation formula for the fractional perimeter and so on and so forth. Okay, I think the last thing is why this exponent, 1 plus s over 2 in the seminorm and not just s, because if I send s to 1, they both converge to 1, right? So it looks a bit bizarre. So with our choice, the scaling of this object is, if I scale the surface, the current by lambda to the n minus 1 minus s, okay? And I write the exponent in this way just because we sort of think that this is the right notion for any codimension, okay? So now, higher codimension is very difficult, and there are many pathologies that can happen in higher codimension, but we want to define an object that scales like n minus k, so the correct scaling of the codimension k mass, plus 1 minus s, so a parameter that goes to 0 as s tends to 1, and this is the correct scaling seminorm that has to be put there. So I write it as 1 plus s over 2. Okay, and I think I'm done. Thank you for the attention. Questions?
Could you summarize what you said pretty quickly? And remember, what you know in codimension 2, what's the status of codimension 2 minimal surfaces?
Oh, so actually there is only basically the definition and the gamma convergence we do. So
You mean the classical or
The classical.
classical.
There's no proof that there's even a single classical stationary minimal surface in a Riemannian manifold. So say it works for two-dimensional surfaces because you can use Douglas-Radu, then you can prove something. But even there, you need some topological conditions. I mean, there are actually some compact manifolds in which it is open to show that there's a single non-trivial minimal two-dimensional surface.
No, I mean, I guess the problem of implementing geodesics is also kind of in that spirit, right?
Right, but I mean, but one geodesic is you can use Birkhoff technique, and so here there's not even a single guy. Okay. I mean, like, okay, so you have a min-max procedure which is producing something, but it spits something which is very irregular. I mean, it spits a stationary varifold, so you will not be able to prove kind of it's a classical object. You can prove some regularity on some set, like, you know, prevalent regularity, but or if you are two-dimensional, you can try to use the classical, you know, to stretch the classical Douglas-Radu. then you can do like the classical work of Karen with Sachs. And under certain topological conditions, you can prove that there is like a two-sphere which is minimal. But you need a little bit of topology. I mean, in particular, I think so there's a class of manifolds. I think the manifolds which are called aspherical, in which any homotopy group is 0, but the manifold is still compact and non-trivial. And I think for those manifolds, there's not a proof that there is a two-dimensional minimal surface which is non-trivial. In other words, there's just not like one single.
You need some topological information.
Yeah, and I mean, and if you instead drop, say, 2D, say you want to show that in a 5-dimensional manifold there is a 3-dimensional minimal surface, then there's just simply not even a sensible approach to the problem. Like, there is a sensible approach to the problem, but the object that you get is pretty weak, and then you cannot prove full regularity.
So the dream would be to sort of approximate this object with, so at least in low dimension, because, so let me be clear. In codimension 2, I do not expect that if you take a critical point, but even stable or whatever, or locally minimizing of our object, then the singular sets of the surface is smooth. Okay, I think that the best that you can get is as the classical, so codimension 2 of the surface, so codimension 4 of the ambient. Okay, and so for example, if you take dimension 3 in a 3 manifold, I would expect that so I think we will be able to do this in like 1 or 2 years. What would
you be? Sorry, what are you going to do in 2 or 3 years? What?
Yeah, so in my mind, the first step is take a 3-dimensional manifold, so do the regularity of this object for n equals 3, and prove that if you do a min-max, the singular set is smooth. Okay, so I get a fractional harmonic map that is for which the singular set is a C1 alpha graph on whatever. Yeah. But then the step of sending S to 1 will be very difficult.
Okay.
Of course, the minimizers in that case, you're not smooth. They could have branch points, for instance. And stability doesn't give you any, unlike for hypersurfaces, stability doesn't give you any a priori estimate. So which is the reason why in higher codimension the problem is very open. Okay, thank you.